Welcome to module 38 of database management systems. In this module and the next, we will talk about query processing and optimization. Of that, in the current module, we will talk about query processing. So, in the last module, we had talked about database recovery, and now we will try to understand the overall flow of processing queries. So, if I fire a query like select from where, how will that actually access the database files, the B trees and indexes and so on, and compute the result is what we would like to discuss. And a query can be processed in multiple ways, giving rise to different kinds of costs in terms of the time required for processing the query. So, we will define certain measures of query cost, and then we will take a quick look into a set of sample algorithms for processing simple selection operation, sorting, join operation, and few of the other operations like aggregation. So, first let us, so these are the topics to talk about, and first we will take a look at the overall query processing algorithm. So, this is the flow. So, this is a way the query will get processed. So, here what you have is this is where the input query comes in. Naturally, it is written in terms of SQL, which is kind of a programming language. So, you need a parser and translator. So, it is parsed, translated, and it is translated into a relational algebra expression, as we have shown at the very beginning, discussed at the very beginning, that SQL is basically derived or developed based on relational algebra. So, corresponding to every SQL query, there is a one or more relational algebra expression. So, you express in terms of that, then you optimize, you try to see how the relational algebra expression can be made efficient, and to optimize this, we might use some information about the statistics. Statistics in terms of, we might use the information, past history information of say what is what are the attributes on which more often the where conditions are put. We might want to use statistics like how many tuples actually exist in the relation right now and so on. And based on that, we will decide on an execution plan. Execution plan is how we actually want to, what are the actions that we actually want to do in terms of accessing the different indexes and the different B plus tree nodes to evaluate the query, and that is the job of the evaluation engine. As you can see that it will access the data for that, and finally, out of that the query output will be generated. So, in this module and the next, we will take a quick look into glimpses of these steps one by one, and try to understand how query processing and optimization can happen. So, beyond parsing and translation, there is evaluation, as we have talked of. Now, if we take in terms of say a query where select from where clause has been translated. So, for example, if this is we can simply write out, say if we have select and what are we selecting here? We are selecting salary, and where are we selecting it from? The from is instructor, and under what conditions are we doing that? Where is salary is less than 75,000. So, if you had a query like this, then you know that it will be it will get translated to some kind of a relational algebra expression like this, where you do a selection on the salary, and then you do a projection on the salary, and then you do a selection based on that condition. Now, it is also clear to see that this particular relational algebra expression can be equivalently written by swapping these two conditions. That is, we can first do a selection and then do the projection. they are actually equivalent and there could be multiple equivalents. So, we know that given a query there could be multiple relational algebra expressions, and then the relational algebra expression, the operations can be evaluated also in one of the by using one or more different algorithms. So, basically what you have different options given a SQL query, you have different possible relational algebra expressions that are equivalent. Given every relational algebra expressions, you have different strategies, different algorithms to actually execute and evaluate that. And we would like to, based on these, we would like to annotate the expression. We would like to mark out as to whether from the above two, say whether we first project on salary and then do the selection, or we first do the selection on salary less than 75,000 and then project. And with that annotation, we will build up a total evaluation strategy, which is known as the evaluation plan. And for example, here we can have different strategies, like we can use an index on salary, and if you use that, that will be it will be pretty efficient to find tuples which satisfy salary less than 75,000. Or we can scan the whole relation and discard all those instructors for which salary is greater than or equal to 75,000. So, there could be different ways in which we can do this evaluation, and that is what optimally has to be decided in every case. So, in terms of query optimization, out of all these equivalent evaluation plans, we try to choose the one that gives us the minimum cost, the lowest cost evaluation. So, the cost will have to be estimated based on certain statistical information from the database catalog. For example, number of tuples in the relation, the size of the tuples, the attributes on which frequently condition are tested, and so on. So, this is what we would in totality try to understand. Out of that, in this module, we will first define what is the measures of cost and look at the algorithms for evaluating some of the relational algebra operations, and then you can combine them to do bigger operations. And in the next module, we will talk about the optimization. So, first let us see how we define the cost, because if we want to say that we can do it say in 2-3 different ways, evaluate the same query in 2-3 different ways, then we must assess as to what is the best way of doing it, and the best way is whatever gives us the least cost. So, the measures of cost will be in absolute terms, it is in terms of the elapsed time, how much time does it take. And there could be many factors which dictate that, because in terms of evaluating this, we will have to access the disk. So, access time of the disk will be involved, the computing time in CPU may be involved, even some network communication may get involved. So, out of these, if we assume that there is no network communication cost, just for simplicity, that is everything is connected to a very high speed network, then between the disk cost and the accesses and the CPU processing cost, the disk access is the predominant cost, because and it is relatively easy to estimate that, because as we have looked at the storage structure, we know that it is a typically a magnetic disk where the head has to move to the correct cylinder to find the block where the records can be located. So, there is this process is called the seek. So, we will need to find out estimate how many seek operations we need and multiply that by the average cost of seeking a block. Similarly, while we are reading that, we need to estimate how many blocks to read and average cost to read a block, number of blocks to write, average cost to write the block. Cost to write the block is usually greater than the cost to read. Actually, often when we write some data, after writing we also usually read it back to make sure that the write was successful. So, these are the typical cost factors that will dominate. So, if we say that if we just count the number of block transfers and the number of seeks, and if the time to transfer one block is T t and time for seek is one seek is T s, then the cost of transferring B blocks doing S seek will be given by this expression. You can easily understand that. So, every block transfer is T t and the B blocks being transferred. So, this is the transfer cost, and if there are S number of seeks and every seek time is T s, then this is the seeking cost, and adding them together we get the total cost of seek and transfer. For simplicity, we will ignore the CPU cost, and we will also for now not consider the cost of finally writing the result back to the disk. We will simply check as to what will it take to actually compute the result. So, there are also, it has to be noted that there are also several algorithms to reduce the disk I/O. We can do that by using extra buffer space. For example, one block has been read in and we are just using one record of that. If in the next operation we have to use some record which is already existing in that block, and if that block is maintained in that buffer, then we do not need to go back to the disk and actually read the block once again. So, the more of the buffer space that we can provide, naturally the performance would become better, but certainly that means that the memory required for keeping the buffer would be higher, and it is also often difficult to decide as to estimate a priori as to if I am looking for a particular block, whether it is already there in the buffer, so that the I/O can be avoided, or it needs to be actually read back from the disk. But these are some of the cost measures that are used in a more sophisticated cost function, but we will simply use the seek and read cost from the disk in terms of blocks to estimate our cost of the different operation. So, let us look at sample algorithms for different basic SQL operation. So, the first and most common SQL operation is selection, as we all know. So, the selection we discuss in multiple algorithms for different situations. The first algorithm is here we are calling it as algorithm A1, is a linear search. So, what we do, we just need to do some selection. So, we scan the, say we are looking for a result of a couple of records and or a single record, then we just scan the file from one end to the other. We look for all the records and check whether they satisfy the selection condition. So, the cost for that would be BR block transfers. If there are if BR is a number of blocks containing records from relation R, then BR blocks have to be read and one seek has to happen. Now, if the selection is on a key attribute and we can stop finding the record, then on the average we can expect that we will be able to find it by having read half of the record. So, BR by 2 block transfers plus 1 seek. So, if I write it in the notation that we had used earlier, it is BI by 2 into the transfer cost plus 1 seek cost. So, this should give us the cost of the finding out the particular record from any file if we are doing a linear search, if we are doing a linear scan. So, the advantage of this is it can be applied irrespective of the condition, ordering of the records, whether or not the index is available and so on. So, this could be the fallback in any case when we want to do that. And just you may note that in memory when we search, we say that we will keep the data sorted and binary search is efficient, but that is not the case for us here, because as you know the data is not stored sequentially, it is in terms of a tree structure. So, when the index is available, we will do the index based search, otherwise we will have to do some kind of a linear scan alone. So, this was the first algorithm that we can think of. Now, let us assume that it is the situation is such that we have some index on the B tree, B plus tree that we are using to going to do the selection on, and let us assume that h I is the height of that B plus tree. So, the second algorithm is good if we are using a primary index and we are looking for equality on a key, that whether it matches certain key. So, what we will have to do? We know that in B plus T, if the height is h I, then we will be able to find the leaf node surely by h I number of block transfers, because we will be h I is the height of the tree. So, this is the number of nodes, the number of blocks that we will need to read. So, each one of that will take a transfer time plus a seek time, because they are not consecutively located. So, every time they will have to be we will need to seek them. So, that will be h I times T t plus T s, and we will need one additional block transfer to actually get the data, get the record read in. So, that will give us the cost that we have shown here. In a variant of this algorithm A 3, we may be using a primary index, but we are looking for equality on a non-key. So, if you are looking for equality on a non-key, since it is a non-key, then certainly in the result we may have multiple records, but the records will be on consecutive blocks, because we are using a primary index. So, if B is the number of blocks containing matching records, then we will need to have, say, this is a cost to find out the first one, and then from consecutively thereon we will need to locate the next record and the B blocks for transferring all the matching records. This is the kind of cost that we will need to go through. Naturally, you can see that in these cases all these cost expressions are better than what we were getting in terms of doing a linear search. If we look into a few of the other situations, for example, let us say instead of primary index, if I have a secondary index and you are looking for a equality on non-key, then you can retrieve a single record if the search key is a candidate key. If it is a candidate key, then we know that even though it is not a primary key, but certainly two tuples can never match on them and still exist. So, if it is a candidate key, we will need to have, we will get only a single record, and therefore, this is a cost expression that you will get. But if it is not a candidate key, then there could be multiple records that will have to be finally retrieved. So, if there are n records, then first you will need h I to locate the first record, and times, of course, h I times the transfer plus seek cost, and if there are n records, then you will need to every time each one of them, because they are on secondary index and non-key. So, you will have to retrieve them one by one, and every time you will need a search, you will need a seek and transfer time, and this can, as you can understand, could be quite expensive if n turns out to be large, which will often be the case. We can implement different, this is a very common selection condition, where we have these kind of conditions that we are selecting on less than equal to or greater than equal to kind of condition. So, we can implement this using a linear file scan or by using indices in a certain way. Using indices, we will certainly have a better performance. So, if we have a primary index and we are using comparison, then what we can certainly decide is we need to find out the first tuple which matches this condition, that is A is greater than equal to V. And then once we have found that in a primary index, the following ones will all be ordered in that manner. So, I can scan sequentially from there and get them. So, finding the first one will give me finding the first one will take this cost, because I am doing a search on the primary index, and then if there are B blocks containing the result records, then this is the cost that we will need. Whereas, we can do something different also, we can just start sequentially based on the primary index from the beginning and check for the till we get a tuple which is greater than V, and then we do not use the index. We can simply we know, because these are all ordered in terms of the primary index. So, that will be the search result that can be easily produced. So, here we are using a linear scan, and that itself will give a good result. But if we are doing a similar operation based on a secondary index, we are doing composition on a secondary index, then we will again use the index to find the first index entry greater than equal to the key value and then scan the index sequentially. So, we will get a cost which is similar to what we saw earlier. And in the other condition, we can just scan the leaf pages of index, finding the pointers to records till the first entry. So, we are doing a more a sequential one. So, in either case, retrieving records that are pointed to requires I/O for each record, because they are on a secondary index. So, they are not necessarily consecutive and residing on the same blocks. So, they may be all distributed across different blocks, and in such cases it may turn out that actually doing a simple linear scan may turn out to be cheaper. Often we have select conditions which are conjunction. So, it could be conjunctive select and maybe using only one index. In that case, it depends on if there are n conditions, then we will need to be depending on the combination of this condition theta I and the algorithms that we have seen here, we can evaluate as to which strategy will give the least cost for this condition. So, we will do the access based on that, and then once we have accessed the tuple, then we will try out the other conditions on the tuples that have been fetched into the memory buffer. You can also do conjunctive selection using composite index. We can, there are depending on the attributes involved in theta 1, theta 2, theta n, we may have a multi key index, and that decision of course, as to whether I have a multi key index or what is that multi key index is of course dependent on the earlier statistics, but if we have some multi key index which are appropriate composite index, then we can use that and more directly get the result, which will be more efficient. Or we can do conjunctive selection by intersection of identifiers which require indices with record pointers, and we will use corresponding index for each condition and then fetch the records, which is simple to understand. Disjunction, that was conjunction. If we want to do disjunction, then if we have all conditions, all of these conditions have index on them, if it is available index, then we can do something better. Otherwise, if we do not have that, then it is better to do a linear scan, because the conditions all tuples which satisfy theta 1 will be there in the result, those which satisfy theta 2 may or may not satisfy the others will also be there, and so on. So, what we can do is if we have index on each one of these based on each one of these conditions, then they can use corresponding index for each condition, get the results and take their union and then fetch these records. So, these are some of the. So, I just gave you a quick outline in terms of some of the different algorithms that selection could use. Negation of a condition could also be done, but it usually requires a linear scan on the file, that is there is not much optimization that you can think of here. The next operation which is often required may not be explicitly, but in terms of doing other operations is sorting. So, if we may build an index on the relation, then we can use that index to read the relation in sorted order. This is what we have already discussed, that b plus t in the in order traversal will always give you the sorted order. So, that may lead to one disk access for each tuple at times. Now, if the relation can totally, if all the records can totally fit into the memory, then we can use some in memory algorithm like quick sort, but often that will not be the case, relations are much bigger. So, what we will have to do is we will have to take recourse to external sort and merge strategy, which is a very old strategy, but very effective. So, just to illustrate that, suppose suppose this is the initial relation. So, what we do, certainly we cannot read that whole relation in terms of memory into our memory. So, what we do, we take different parts and say we are taking in groups of 3 just for illustration, and make them and sort them in memory. So, take them. So, take that many records which you can fit into the memory and sort them. So, once you have sorted them, then you can these are two sorted sublists of the original set of records. So, now you can merge them according to the merge strategy. So, this is the simple merge sort strategy, and again you write this back. You do the similar things again here, write them back. So, now you have two bigger sorted lists. So, these are called runs. So, the first step creates the runs, and now after you have done merging once, you get longer runs. Then again you merge them into a bigger run, and depending on the actual size of the file and the size of the memory that directly fits in, you might be doing multiple such runs till you get to the sorted output. So, that is a very external sort merge is a very effective strategy that the databases will always use, and the efficiency of that or the cost of that depends on the size of the memory in terms of pages as to what can fit a complete one run data. So, this is whatever I have described is simply given here in steps of algorithm. So, that is a sort, that is a here is a merge. So, you can go through that and convince yourself that this is what the algorithm is actually doing. And there are two cases you have to consider, whether your data fits into the memory, otherwise if it does not fit into the memory, then multiple passes are required, and these are the steps of the algorithm that will be followed. Now, next to sorting, certainly we have often talked about that join is a very required operation in relational database in terms of SQL. So, let us see what it will take to do a join. So, first we talk about, so the join could be done in several ways: nested loop join, block nested loop join, index nested loop join, merge join, hash join. So, these are different strategies of doing join. We will just illustrate the algorithms for the first three strategies. So, nested loop join, what we are trying to do is very simple. We have two relations. We have two relations here, R and S, and we have a condition theta, and we are doing a theta join. So, what needs to be done in terms of theta join? In the relational algebra, what do? We do a Cartesian product, and then in the Cartesian product we check out this theta condition. So, the basic Cartesian product is all records of R will have to be matched, will have to be connected to all records of S. So, that naturally can be done using a nested for loop. So, for each tuple in R, you try out each tuple in S, take the TR-TS pair, and if they satisfy the condition theta, then they go to the output, otherwise you leave that, otherwise you discard that. And here we say R is the outer relation and this S is the inner relation. So, naturally since you have to examine every pair, this could be quite expensive to perform, and the cost may be quite high. So, if we look at what could be the possible cost. So, if n r is the number of records in relation R and B r is the number of blocks in which they exist, then for every record you have to actually access all the blocks of the other for every tuple of relation R, you have to actually access all the blocks of relation S. So, you get this, and you have to access all the blocks of relation R. So, this is the kind of block transfer that you will get, you will require, and naturally you will require so many seek, because every time you have to find out, you have to go and seek for that. So, one optimization that is very common is what you can do is, if the smaller relation can entirely fit into the memory, then you do not need to do this repeated read for that both the relations. So, if it fits into that, then the cost will significantly reduce to BR plus BL block transfers, because the smaller one has already fit. So, you just need to access one relation. Once you need to read the smaller relation and put it in the memory, and then you just need to read the other relation one after the other. So, BR blocks of that, and so you are seeking only twice, one for reading R, one for reading S, there are 2 6. So, here I have just shown a simple example of computing the join of student and takes. So, let us say student has 5,000 records and spread over 100 blocks, takes relation has 10,000 records spread over 400 blocks. Then if you apply the formula above, you will find that if student is an outer relation, you have so many block transfer and so many seeks. Whereas, if takes is the outer relation, then you have so many block transfers and so many seeks. So, you can understand, you can see here that if you make student as the outer relation, then you have much larger number of block transfers, though you need to do less number of seek. But but using takes as outer relation, you have much less block transfers, but more number of seek. Usually seek is less expensive than less costly than the block transfer. So, we will possibly with this kind of a statistics, if it is available, then we will possibly take takes as a outer relation and student as the inner one. You can refine this strategy by doing a block nesting, that is instead of taking every tuple of the relation, you can take every block of the relation. So, for every block of relation R, you try to match with, you try to combine with every block of relation S, and then within every block of relation R, the block B R, you take tuple, and within B S you take T S, and then you do whatever we are doing earlier. But naturally, you get a much better performance, because you are now optimizing based on the block reads only. You are not reading every tuple every time you need. So, I will not go through this simple algebra to show that if you have a memory size of m blocks, then your cost will significantly decrease, and but the larger the m, your cost will come down by a factor of this m. So, block nested loop join will usually be far more efficient than the simple nested loop join. The third strategy, which we will use very often, is efficiently applicable if you are if your join is a equi-join or a natural join, as we have seen that we often need to do a natural join. So, there are two attributes between these two relations, on which during join the values that they match are retained, the values that they do not match are not retained in the natural join. So, if we now assume that we have an index available on the inner relation, then every time we go with the outer relation, we will be able to access the inner relation very efficiently, because for each tuple in the outer relation, the index to look up the tuples in S will satisfy the condition will be found very efficiently, because they are indexed. So, they will occur if through the index I can find them in terms of the consecutivity. So, the cost in that case will turn out to be very simply the cost of the B R, which is the outer relation, the number of blocks in the outer relation, the seek and transfer cost of that, and then the number of record times the estimated cost of a single selection using the join condition. So, we often use the nested loop join whenever we have to do equi-join or natural join. So, here is an example with the same students and takes example. So, it shows that the cost of block nested join, if you work out for the block nested join, then you have so many 40,100 block transfers and 200 seek, whereas if you do indexed one on the assuming that the smaller relation, the inner relation has a index, then you have 25,000 block transfer and seek. So, this will turn out to be a naturally more efficient way of implementing the join. So, these are there are several other strategies, particularly hashing based strategies, merging based strategies, which we are not discussing here, but there are different strategies through which you can do join in more and more efficient manner. Couple of other operations which are often required is duplicate elimination, because if we know that there are duplicate records cannot be kept, duplicate in the sense the records which match in the key field, and a duplicate will often happen in terms of the result, they will happen in terms of when we do projection. we will need to do aggregation, set operations, outer join and so on. So, the first three we will quickly outline. So, duplicate naturally can be very easily eliminated through sorting. They can be done through hashing also, because if we sort, they will come on side by, they will come consecutively after the sort. If we hash, then they will necessarily hash to the same value, which becomes easier to check whether they are identical or not. If whenever we are doing projection, we can project on each tuple, and then you can perform a duplicate elimination to actually get to the final result. Aggregation group, that is whatever you do group by kind of. So, aggregation is certainly will be efficiently done if you have again done sorting, because if you are grouping by something, then if you have sorted on that, those elements will come together, and or if you are hashing, then they will also come together. So, you can easily do the computation on that. And what you can do is, instead of, for example, you are doing a count or you are doing a minimum, maximum, sum, this kind of, all of these are associative operations. So, you can do it in parts, that if you have done in this sorted order, in the hashed order, if you have done the sum of 10 records, then you can actually do not need these 10 records when you do the sum for the next 10 records and so on. So, in this manner, the aggregation can be efficiently implemented. So, we can for average keep sum and count and divide the sum by count at the end and so on. So, we have in this module, we have just given a very brief outline of what are the steps involved in query processing, and what are the measures that define a query cost typically. And we have talked about some of the simple algorithms for selection, sorting, join and aggregation operations. In the next module, we will talk about elementary optimization strategies for processing of queries.